Our ninth objective in Practice Test B deals with solution stoichiometry, which is a double replacement reaction with water as the driving force. When we integrate the stoichiometry in with the double replacement, we call it titrations or solution stoichiometry problems. In our first problem, we're asked to calculate a volume of a 12 molar hydrochloric acid needed to completely neutralize the 5 mils of a 4.2 molar aluminum hydroxide solution. We will begin by coming up with our balanced double replacement equation, where an acid will neutralize the base, producing a salt and a water. Our acid is hydrochloric, written as HCl. The base is aluminum hydroxide, and based on charge, we get AlOH taken 3 times with aluminum's +3. We can see the driving force as HOH, a water molecule, and when aluminum hooks to chloride, we get AlCl3. Acid and base will neutralize, producing a water and a salt called aluminum chloride. I like to tabulate what we know and what we're looking for under the acid and base. We're being asked to calculate the volume of a 12 molar acid solution. We're given a volume of 5 mils and a 4.2 molar base solution. How many mils would be added of the acid to completely neutralize this amount of base? The ingredient that we have both sets of numbers for, molarity and volume, is what we call our given. And what we want to know is the volume of acid. Perhaps a nice little margin note here is to remind ourselves about the equation for molarity. Moles per liter is the equation representing the concentration unit molarity. And we know that in the stoichiometry, the heart of our problem is a mole ratio. In our first step, given the amount of molarity units and liters, we can calculate the number of moles of base. So in our first step, we'll write down 4.2 moles of aluminum hydroxide in every 1 liter of solution. Moles per liter giving us the very definition of 4.2 molar units. I'll multiply that by the volume, but in a liter unit, 0.005 liters, and just set that over a 1, and you can see now how the liters have canceled. Molarity times volume of given is step 1 of our stoichiometry journey. We're now ready for the heart of our problem, our want over given ratio. We want to know the acid. 1 mole is its coefficient, set over the 3 moles that we're going to need here. I got to back up and balance. Here's what I'm noticing when I get to the heart of the problem. We forgot to balance. Back to the drawing board. Let's see, we've got 3 base ions, and that's how I caught myself with my mistake. I forgot to balance. This 3 H's are going to require 3 OH's to completely neutralize. So we've got 3 neutral water molecules. What I noticed as I was getting ready to put in the heart of my problem, I better have equal number of H's as OH's in my heart of the problem, that ratio. It takes 3 moles of the acid to neutralize every 1 mole of our base. The reason I caught my mistake in balancing, the number of H's had better equal the number of OH's to be completely neutral. So the ratio is 3 over 1. So in step 1 of our journey, we took molarity times liter. Step 2, we set up the heart of our problem. And now in step 3 of our stoichiometry journey, we divide, and I don't care if it's volume given and looking for molarity or molarity given looking for volume. In that third and final step of our journey, what we're wanting is going to be placed on the bottom of our fraction. 12 moles of HCl set over under 1 liter of HCl will cancel that and bring us to the volume units that we're looking for. So with stoichiometry that involves titrations, step 1, multiply molarity times liter of given. Step 2 is your ratio. Step 3 will always be divide. And when we do so, we'll get liters of our HCl. And let's hit and see if we get a common answer. And I really wouldn't mind some calculator buddies. So let's hit 4.2 times 0.005 times 3 divide by 12. And the volume is quite small, 0.00525. I'm going to multiply that by 1,000 and report mine in a milliliter, which seems to be a friendlier number, 5.25 milliliters of HCl. 5.25 mils of a 12 molar acid will neutralize 5 mils of a 4.2 molar base. Let's take a look at our second equation. If a student performed a titration and found it took 15 mils of a 4.5 molar solution of nitric acid, our first ingredient, HNO3. We're neutralizing that with barium hydroxide. Barium is a +2, so when we write its base formula, we get BaOH taken twice. We can finish the equation and already predict the coefficient in front of that acid. To completely neutralize, the number of OHs had better match the number of H's to produce an equal amount of water. So we can see that 2 waters will come out, and the salt would be called barium nitrate, BaNO3 taken twice. Let's tabulate the information provided. We have 15 mils of a 4.5 molar acid solution. This will be called our given. It's what we have both numbers for. We're going to neutralize that with 90 mils of barium hydroxide, and we'd like to know the molarity. So this is our target, what we want. In our first step of the stoichiometry journey, it's molarity times volume of what's given. So if we know 4.5 moles of the HNO3 are contained in every liter of solution, 4.5 moles per liter, multiplied by the volume in a liter, so I'll write that as 0.15 liters. We can cancel the liters and be at the mole. We're in the heart of our problem. We want to know the base. Its coefficient is a 1. Set over the acid, its coefficient was 2. So our stoichiometric ratio is 1/2. And in the last step, as we stated before, whatever it is that we want to know, the number provided, either the volume or the molarity, will be placed on the bottom of our fraction. So that 90 milliliters will output in as a liter, 0.09 liters of our base. And you can just set that under a 1 so you can see the fraction. We've canceled out liters of acid, moles of acid, and when we hit, we'll end up with molarity of our base, big M. And hit with me so I get a double check. I'll hit starting with 4.5 times 0.015, divide that by 2, and divide again by 0.09 liters. And I found 0.375, but I'll wait for some nods. Thank you. 0.375. And one more in this set. How many grams of chloric acid are necessary to neutralize 3.5 grams of barium hydroxide? Given a mass, calculate a mass. This is old school. This is just a straight mass problem from a long time ago. When chloric acid, ic comes from 8, so I look up chlorate, which is HClO3 for chloric acid, neutralizes barium hydroxide, BaOH taken twice. Again, we can already predict the coefficient on the acid by seeing 2 base ions. We know that the coefficient in front of the acid needs to be a 2. Same number of H's as OH's. And we can see 2 water molecules forming, and the salt would be barium chlorate, BaClO3 taken twice. We'd like to know how many grams of the acid are needed to neutralize 3.5 grams of a base. Given a mass, calculate a mass. We called that the 3 steps of stoichiometry. So not a titration problem, but an old mass. And friends, you can count on that pattern on the test day. The first 2 will be titrations, and the last one will be just a straightforward mass, kind of integrating an old school problem there. So let's start with what's given, 3.5 grams of barium hydroxide. I like to get my conversion parentheses ready so I can see my target. We'd like to get to grams of our acid, HClO3. So we need a molar mass. Let me do that for us. Barium, 137.3 on the barium, plus 16 times 2 for the oxygen and 2 more for the hydrogen. Looks like our base has a molar mass of 171.3 grams in every 1 mole. In the heart of our problem, we want over given, where the coefficient of our acid is a 2, coefficient of our base is a 1. So we divide, ratio, multiply. In the classic mass example, I'll add up a molar mass for our target, 1 for the hydrogen, 35.5 for the chlorine, and 16 times 3 for the oxygen. Looks like 84.5 grams for every 1 mole. Alrighty, so divide, ratio, multiply. Let's give it a whirl. Somebody hit with me and do my double checking. Times 84.5. I found 3.45 grams. Thank you. 3.45 grams. And let's do it. Give yourself an A+. It just feels good.